Good afternoon again, everybody. It's Evan Stamon here for Umukuloko, Making a Difference. It's our second lecture in the calculus chapter. We are now going to be looking at how the limits that we learned about in the last period apply to the gradient formula. So the first thing we want to look at is if I was to give you f of x equal, let's say, x cubed minus 13x plus 12, and I said to you, find the gradient between x equals 3 and x equals 2, what we're going to do is we're going to say, cool, we are going to put 3 in, get 27 minus 39 plus 12, and get a value of 0. Put 2 in, get a value of 8 minus 26 plus 12 of minus 6, if I get it correct, and therefore say, as a result, the gradient is y2 minus y1 over x2 minus x1 equals 0 minus minus 6 over 3 minus 2, and get an answer of 6 over 1, which is 6. Now, again, I know that many of you guys would want to say, but hold on, I would like to use the idea of m equals the change in y over the change in x. And I'd like to look at that for a moment, because we can see, hopefully, that here the change in y was minus 6, and here, because we went from 3 down to 2, the change in x, sorry, let's just create a little bit more, bit neater there. The change in x was minus 1. So we're going to, again, get the same idea of minus 6 over minus 1, which is 6. And again, it should not surprise you that these two different methods gave us the same result. However, what I would like to talk to you about is effectively what we have here is a cubic function. And we are talking about the gradient between points 2 and minus 6 and the point 3 and 0. Now, somewhere in here, we have a set of axes, granted. Okay, so somewhere in here, we have a set of axes. And again, we have a situation where there is x, there's my origin, there is y. But the key concept we have here is that we have this graph that is doing something along the lines. And the key thing which we have here is we have a function that is not straight. It is curving. Okay? It is curving in some manner such that what we've actually calculated is not the gradient, even though we use it as such. What we've actually calculated is the average gradient across those 2 points. And so the problem we have here is that we are not actually, at this point in time, calculating the gradient. What we're actually calculating is an average gradient. Okay? This function could have curved downwards, it could have had 15 zigzags, it could have had a sine-like curve, it could have been undefined in between here, there could have been asymptotes. We don't know what's happening to this function other than that we are calculating the average gradient across those 2 points. And so, although up till now we've largely got away with simply saying gradient, because when we had a straight line, we knew that the gradient was always going to be the same. Hence, we could use y equals mx plus c. But we couldn't do that with parabolas because the gradient in a parabola kept changing. So what I'd like to look at again is this idea of when we had a straight line, okay, and we looked at this idea of a straight line, okay, we could say y equaled mx plus c because the gradient at any one particular point was m. The gradient at any one point was m. The gradient didn't change. And so we got a little bit lazy by saying the average gradient handwriting again is taking a bit of a beating here, so let me quickly just tie this up for you. Okay, the average gradient, and we got a bit lazy, and we stopped saying the word average because the gradient was always going to be the same. However, as soon as we moved on to curves in the grade 10 syllabus, and we started looking at curves, sorry, wrong color, let's pick a different color. As soon as we went on to whether it be a hyperbola or whether it be a parabola or whether it be an exponential or whatever the case is, this idea of the gradient changed. And so what we can see here is that were we to have a function that did something like this, that in the different zones, up to perhaps, let's call it here we can see that the graph is largely going uphill. And so here we've got an increasing function. Again, to the right of this dip, we have got a graph that is largely heading uphill and is increasing, but in between these 2 points, it is a decreasing function. And we can see that actually the amount by which it decreases is changing. In fact, it's getting steeper, then it starts flattening out a bit. And so this idea of this slope, which is another word that we very often used for the idea of gradient back in grade 8, or sorry, back in grade 9 or grade 10, or this idea of steepness itself is a variable. It is changing. And in fact, as you move across the graph, it changes. So in the one zone, it is increasing, the other zone is decreasing, the third zone is increasing. But the one thing that it seems to be happening is it is changing the whole time. As a result, we cannot talk about the gradient. This idea of the gradient no longer exists because it isn't a constant. Okay? So when we had a straight line, we had a constant gradient. Okay? But now we have a gradient that is a variable. Now, this is where calculus comes into its own. Calculus, this idea of the calculus, the small measurements, the measurements over small distances, becomes very, very important. Because I would like to look at what happens if I looked at the following graph. And so what I want to do quickly is look at the following. And I'm going to set up a quick graph, a set of axes. And let's have a look at the following function. Okay, so here is a function. Hopefully I can draw it fairly well. And let's see what happens. Hopefully I get it to draw it fairly well. So it's a bit wonky on the left-hand side. Let's see if we can just get a little bit smoother than that. Okay, so what I want to look at is this is the value here, x equals 1. And here's the value of 2, 1, 0. So let's look at the average gradient. Between x equals -1 and x equals 2, between x equals -1 and x equals 1, between x equals -1 and x equals 0, between x equals -1 and x equals -1. And I hope you are realizing that that last one should pose a problem. So what I'm going to do quickly, just to make my life a bit easier, is I'm going to quickly give the equation I thought of. So this is y equals x squared, simple function. Okay, y equals x squared, nothing fancy. And so what I'm going to do is quickly look at what's going to happen. At -1, the y value will be 1, the y value will be 4. So therefore the gradient will be the change in y over the change in x, which is 2 over 2, which is 1. Now, let's look at what that means. That means that the gradient here, okay, the gradient across these 2 points is 1. What does that mean? That means that the gradient is increasing by one value for every one value upwards for every one value it goes to the right. Now, if you think about it, that has got very little relevance to what's actually happening around here at x equals -1. Okay, at x equals -1, this function clearly is going downhill and is a decreasing function. So right now, the function is, reading from left to right, is decreasing. So this value here of the gradient equals not sorry, not delta equals 1, m equals, okay, this value here of the gradient equaling 1 has got very little relevance at all to what is actually happening in the graph. Okay, the gradient equals 1 is the average gradient across those 2 points, but doesn't tell me much about what's happening at that point, x equals -1. Okay, x equaling -1. Let's have a look what happens when we make x equal to 1 and -1 and 1. We're going to get y equals 1, y equals 1. So the gradient would be 0 over, it's not actually over 2, I'll fix that now, over 2, which equals 0. Sorry, again, I see I've made a minor error, so let's go and fix that quickly. That would have been, the gradient is, the change in y is, I was right. Sorry, I do apologize. Okay, cool. Now, what we have here is a situation where, wonderfully, across here, the gradient is 0. So here the gradient equaled 1, here the gradient equaled 0. Now, what you might notice is there's a pattern itself in what's happening as I move my x values closer to x equals -1, i.e. what we're talking about here is the limit as x tends to -1. Okay, and as this is happening, what we are noticing is that the m value is decreasing. You might want to put a little more detail on it. You might want to try a guess, but we can see that the m value is decreasing. Okay, we can try it again and confirm our thoughts. We put this out as a hypothesis. We can now see that actually in this value, the m value dropped from 1 to 0. And what's going to happen now is we look at it again. We've got y equals 1, y equals 0. So therefore, the change in, the gradient will equal the change in the change in y, which is going to be -1 over 1 equals -1. And what you may see here is that previous statement of the gradient is decreasing has continued. More importantly, you may have seen it's gone down in a regular pattern, and that might lead you to this thought, and I'm just putting it out there as a thought, that therefore this gradient, shouldn't it equal to -2? Because if you've gone from 1 to 0 to -1, shouldn't we now go down to -2? But we know we can't do this because actually we've got a big problem. And it's not just a problem of something you can solve, we can deal with easily. What we actually have here is a much bigger problem than that. And so what I'd like to look at is what the problem actually is. Because if x equals -1, I'm going to have y equals 1 and y equals 1. So m will be 0 over 0, which is such a weird thing that it's not even undefined. It is what we call indeterminate. And so we really have a large problem here. Okay, we think it should be -2, but actually it is such a weird thing that we can't even give it a real handle, a real name, other than to say that it is indeterminate. We can't even determine if it is undefined or not. However, let's go back into safer waters. Let's look at the average gradient between, let's pick blue pen again, so we can have our notes being consistent, between x equals -1 and x equals -2. So now we're going to get y equals 1 and y equals 4. The average gradient across these 2 points, which is now shown by this line, okay, because we're now talking about m equaling -2, will now be the change in y, which is 3, over the change in x, which is -1, and so we get a value of -3. Now, that poses a problem, because if we'd followed this pattern, then we would have gone m equals -2, m equals -3, and everything would have been happy, except for this problem of we can't have naught over naught. And so what they do is they try to do something which is quite clever. And they start doing some maths, as I said, the trickery of the maths of the limits on the previous page, and they start doing something which is quite clever. So please, let's have a look at what they're going to do. If we had a function on a set of axes, doesn't really matter where these points are, and I now had a point here at x and there. So let's call this point here x1 and this point x2. Then this point here would be y1 and this point over here would be y2. You can see hopefully that those things are in line. And you know what, for want of a better description, I'm going to have this function do something like that. Okay, it's not massively well drawn. I apologize for that, but I have a function that's doing something along those lines. Hopefully what you can see is that the gradient keeps changing. However, the average gradient between these two things is our stock standard formula of what we had here just now, of our average gradient we are used to calling m is simply y2 minus y1 over x2 minus x1. What I'm going to do now is I'm going to change the notation ever so slightly, and I'm going to choose to hopefully take that, copy it, and paste it down here. And hopefully what we're going to get now is, so let's control that. So I don't know what's going on here. Okay, sorry, let's go back to where we were. Okay, and so what we have here is a situation where if I was to look at the same thing again, okay, what I'm going to choose to do now is I'm going to choose to look at the same thing using functional notation. And so if this is now my curve, such that I have the red line doing something along those lines, okay, but this time I'm going to call it f, okay? So in other words, y equals f of x. Well, the one key useful idea here is that if this is x1, then the whole point is that this now is f of x1. And if this here is x2, then this here would be f of x2. My gradient is the same line as it was just now, okay? But what's happened is I've changed the notation. All I'm doing right now is showing you how, by playing with the notation, I can get to some useful ideas. So my gradient is now f of x2 minus f of x1 over x2 minus x1. But because they are still measuring over 2, it is still an average over 2 points. It is still an average gradient. We now take out one extra piece of trickery, and this actually is kind of cool. Okay, if you know Joburg and Pretoria, it's the same as saying Pretoria is a city that's 60 kilometers away from Joburg. You don't talk about Pretoria in its own right, so you're not talking about two cities. You're talking about one city and another city's relationship with it. And so what we're going to do is we're going to look at the following, and this is key. I'm going to draw the same function, hopefully, or roughly the same picture, okay, as I had just now. And what I have here now is, again, using functional notation. It's coming through here and doing something along those lines, okay? And it is y equals f of x. But I'm not going to talk about this point here as being point A. And that means that this point here is point f of A. In fact, this point's coordinates will be A and f of A. But what is key here is that I'm not going to talk about this point, not as a point in its own right, but as that point which is h distance away from A. Which means if it is h to the right of A, this is now the point A plus h. See if you can follow that. And if I put A plus h into f of x, that means that this y value here is now going to be the f value of A plus h. Coordinates of this point are A plus h and f of A plus h. I'm still talking about 2 points, so I'm still talking about the average gradient across these 2 points. But what I'd like you to consider is what I now have in terms of my notation. I now have that the average gradient still m is going to be the change in y over the change in x. So all of that is still valid. What I now have is f of A plus h minus f of A all over A plus h minus A. And I know that I've fiddled around with it for a bit, and maybe some of this is bypassing you, but something really, really, really important is about to happen. And that is, if I was to focus on the denominator, that if I was to focus here on the denominator, some of you may have already noticed that what I'm about to get is f of A plus h minus f of A all over the single monomial denominator of h. And the fact that this is h by itself allows me to do something really cool in our next video. And the fact that we've got h by itself, a monomial as a denominator, means I really have a much simpler monomial for the denominator. Denominator is really, really, really important because it allows me to do something really cool in my next video. So at the moment, all we did in this video is we looked at what was an average gradient, the gradient over 2 points. We played around for quite a while with the notation and saw that if we played around with the notation sufficiently, we could simplify it down to a situation where we have a monomial in the denominator instead of always having had 2 terms or binomial in the denominator. And that will be proved crucial in our next video. Thank you so much.